Zener ratio. The Zener ratio is a dimensionless number that is used to quantify the anisotropy for cubic crystals. It is sometimes referred to as anisotropy ratio and is named after Clarence Zener. Conceptually, it quantifies how far a material is from being isotropic, where the value of 1 means an isotropic material. Its mathematical definition is $R equals \frac 2C44 C11 C12 where C id refers to elastic constants in Voigt notation. Cubic materials. Cubic materials are special orthotropic materials that are invariant with respect to 90 degrees rotations with respect to the principal axis, i.e., the material is the same along its principal axis. Due to these additional symmetries, the stiffest tensor can be written with just 3 different material properties like $___mass C equal \begin B matrix C11 and C12 and C12 and 0 and 0 and 0 \C12 and C11 and C12 and 0 and 0 and 0 \C12 and C12 and C11 and 0 and 0 and 0 \0 and 0 and 0 and C44 and 0 and 0 \0 and 0 and 0 and 0 and C44 and 0 \0 and 0 and 0 and 0 and 0 and C44 \NB matrix /quad $. The inverse of this matrix is commonly written as $___mass equal \begin B matrix /T frac 1e and /T frac UE and /T frac UE and 0 and 0 and 0 \T frac UE and /T frac 1e and /T frac UE and 0 and 0 and 0 \T frac UE and \T frac UE and \T frac 1e and 0 and 0 and 0 \0 and 0 and 0 and \T frac 1g and 0 and 0 \0 and 0 and 0 and 0 and \T frac 1g and 0 \0 and 0 and 0 and 0 and 0 and \T frac 1g /NB matrix /quad $. Where E is the Young's modulus, G is the Shea modulus, and U is the Poisson's ratio. Therefore, we can think of the ratio as the relation between the Shea modulus for the cubic material and its isotropic equivalent. $R equals \frac GE equals \frac 21 plus UGE \equa \frac 2C44 C11 C12 Universal elastic anisotropy index. The Zener ratio is only applicable to cubic crystals. To overcome this limitation, a universal elastic anisotropy index O was formulated from variational principles of elasticity in tensor algebra. The O is now used to quantify the anisotropy of elastic crystals of all classes. Tensorial anisotropy index. The tensorial anisotropy index T extends the Zener ratio for fully anisotropic materials and overcomes the limitation of the O that is designed for materials exhibiting internal symmetries of elastic crystals, which is not always observed in multi-component composites. It takes into consideration all the 21 coefficients of the fully anisotropic stiffest tensor and covers the directional differences among the stiffest tensor groups. It is composed of 2 major parts E and A, the former referring to components existing in cubic tensor and the latter in isotropic tensor, so that a T equals I plus A. This first component includes the modified Zener ratio and additionally accounts for directional differences in the material, which exist in orthotropic material, for instance. The second component of this index covers the influence of stiffness coefficients that are non-zero only for non-cubic materials and remain zero otherwise. $I equals I, T plus I, cov equals \frac 2C44 plus C55 plus C66 C11 plus C22 plus C33 C12 plus C13 plus C23 plus \sum I equals 13 \alpha Cg $, where alpha Cg is the coefficient of variation for each stiffness group accounting for directional differences of material stiffness, that is Cg1 equals, Cg2 equals, Cg3 equals. In cubic materials, each stiffest component in groups 1-3 has equal value, and thus this expression reduces directly to Zener ratio for cubic materials. The second component of this index is non-zero for complex materials or composites with only few or no symmetries in their internal structure. In such cases, the remaining stiffness coefficients joined in 3 groups are not null. Cg4 equals, Cg5 equals, Cg6 equals.